Greetings, today we have this problem from Rudin. So we need to show that the radius of convergence Pepper series with the sequence an having sufficiently many integers distinct from 0. Okay, and we have to prove that the radius of convergence is at most 1. So since there are infinitely many ans that are distinct from 0, we could say that the supremum of absolute value of an is greater than or equal to 1. That's something we know for sure. Now let's investigate into the convergence of power series. So let's take the superior supremum limit, the upper limit of and root of absolute value of an. About is going to be equal to the reciprocal of the radius of convergence. Now for it to be at most 1, this has to be greater than or equal to 1. So we have to show that this is going to be greater than or equal to 1. Let's label this somehow. The value, let's call it alpha. Alright. Now if we were to investigate into this, then suppose alpha is less than 1 and not greater than or equal to 1. Well, if alpha is less than 1, then for every epsilon greater than 0 exists a positive integer n such that for every n capital greater than or equal to n capital also belongs to positive integers, we have that supremum with okay, I'm stupid. We don't need to include this part. Supremum n capital greater than or equal to n tiny of square root of n capital to value of n tiny minus alpha is less than epsilon. Now we were to look into this supremum over here. We know for sure that it is an infinite amount of elements so that their absolute value is greater than or equal to 1. So therefore the supremum is greater than or equal to 1. Now we're looking into a different supremum, just like this, and well, if we were to look into that, then we could say for sure that for one this applies for every positive integer, and we could start with capital N greater than or equal to n. This isn't a problem because there's an infinite amount of an satisfying this equation, the equation inequality. Right now, n, since this is greater than 0, then there exists some n for which an is greater than or equal to 1, which implies that the square root and the square root, the end root of an going to be greater than or equal to 1. So the supremum, okay, and I also forgot to include the absolute value here. Alright, now we can safely say that n root of absolute value of an will have this problem greater than or equal to 1. So since alpha is less than 1, this difference is going to be positive. We can just remove the absolute value. What we'll have here is actually, let's call this a problem somehow. Let's call it beta. So beta minus alpha is less than epsilon. Beta is less than alpha plus epsilon. Now recall how alpha is less than 1. It means that between alpha and 1 we can pick some number. Let's call it j, yeah? Less than 1. Next, what we can do is we're gonna say so is equal to j minus alpha. So what we have here is beta less than alpha plus j minus alpha. It's gonna be equal to j, yeah? Now j is less than 1. So beta is less than 1, which is a contradiction to something we know for sure is true. Therefore, by contradiction, we know that alpha is greater than or equal to 1, which implies that 1 over alpha is less than or equal to 1, which is the radius of convergence. Now, this could be scribbled more concisely, but that will be a little bit less rigorous. Now, I did make a few logical leaps, mostly in this section, but it's fairly easy to show because we're working with infiniteness. If this is not going to be true for some n, then it is actually finite, and yeah, well, that's it for today. Sorry for a short video. I have very little time lately, but I'm still trying to roll out something at least. So, bye.